Alright, so this is my lab write-up for kinematics of projectile motion, lab 2. So first, lab objectives: to gain a deep understanding of projectile motion through observation of the effects different angles have on the range, calculate hidden physics values, initial velocity, range, hang time through the application of kinetic equations, to witness the two-dimensional motion of a projectile moving along a horizontal trajectory with only the effect of gravity as its acceleration. So those are objectives that I created. Hypothesis: I believe that calculating the various kinetic values will be difficult in experimental application, especially considering the errors that such experiments can maintain. I also believe that the 45-degree angle will attain the largest range for a projectile. So the second one is just a fact, but I wanted to see if I could prove that through this experiment, so I put it as a hypothesis. And then the first one was just a kind of thought it would be difficult to do it through an experiment. So this is my pre-lab questions. Actually, I'm going to go here. So for part A, what I did was I created a ramp, just like Professor Curtis said, to mark 3 points on it, top, mid, and then closer to the bottom. And then I set it up near the edge of a table, 3 to 10 centimeters away, or edge, giving it edge, and then put paper on the ground, taped it on, and did a plumb line to get the area right underneath where it left the table for measuring purposes, and then did multiple trials for each spot. The ramp was also at a 50-degree angle. So then I did 4 trials per area of letting the marble drop from that height until it dented the paper, and then I measured from that dent to the plumb line spot hole, and then record that value. So here's my values: ramp incline 50 degree, ramp distance, how high the point was, then each trial, these are the measured distances, got the average standard deviation. Here's table 2, that was all those trials, table 3 and all those trials. I punched these into Excel to get the average standard deviation, standard error, except the second one was giving me trouble, so I just did it manually. Average standard deviation and standard error right there. So there's that. Here's a little short video that I did, just showing a time lapse of the process. Then I'm creating the ramp, setting up at a 50-degree angle, measuring the points, do some calculations. Hard to see the ground, but I'm putting paper. There we go. There's the plumb line. We get plumb line, measuring it. Doing the trials, measuring, and marking off. I used more paper because it didn't fall on the same paper, so I had to use 3 sheets of paper instead. Once I got those measurements, plugged them in, got the standard deviation, something like that. Alright. Then for part B, what I did was I set up a similar ruler and bin with the clip, like Professor Curtis suggested, and shot it 5 times up in the air. 5 times up in the air with a slingshot, just using like a little ball. I didn't use the marble because I couldn't find it. I tried to at first, but yeah. So I did 5 of those up in the air, and then picked 3 angles: 20 degree, 45 degree, and 70 degree. That was an accident to do 25 degrees above or below 45. Because then it would get the same predicted range, but I didn't realize that until I had already recorded the values. So anyway, so there's the hang time for the first part of the 5 trials, and then each of the 3 angles got 4 trials. So I record the hang time with help, and then I took from the hang time, I took the final velocity, cut the hang time in half to get the time to fall, and then the final velocity, calculate that through gravity and the time to get the initial velocity. So calculated launch velocity, that, and then got the height through the calculated launch velocity times time plus a half times g times time squared, and that's how I got the height. Then I averaged all these launch velocities out into one launch velocity for table 6. Got the predicted ranges through the range equation, just plugging in the initial launch velocity divided by g times sine 2 times the angle, and got all of those. Again, the predicted ranges are the same on the first 4 and the last 4. Actual range. So then I actually shot at that angle using the ruler device and measured that out in feet and inches and then converted to meters. Got the average range of each of those values. Got those here. And then calculate the percent error through the experimental value minus theoretical value times 100% to get the percentages for those values for each 4 trials. Alright, so as far as conclusions go, I would say that our objectives were successful, that I observed those, definitely understand more about projectile motion and kinematics, and it was a bit difficult to calculate the kinematic values, especially the hidden ones, but once I got it down, I had it. Same process here as what I just described in the table 6. To get table 4, just the average actual range and percent error, just use the range equation again, the percent error equation, and the calculated range, calculated velocity were just the same through. Do you have a picture of it? Yeah, so here through the final velocity equation that we did in the Prelab questions, and then the range equation, and then the percentage error equation. Alright, so then comparing those, it was difficult with the plumb line. I didn't know what I was completely doing with that, so that was probably a potential error. Another potential error was dropping it consistently. That could be an issue. I predict that the paintball pellet, horizontal and just drop vertical, will fall at the same time, hit the ground at the same time. If the ramp is altered, to give twice the initial velocity, then it's going to give twice the horizontal speed, or double horizontal speed. And then describing the acceleration, there's an acceleration here, just to spell that out a little bit. And then for the last 4, we did encounter a lot of error, so our hypothesis about the 45-degree angle being the longest range, it actually wasn't proven due to a large amount of error. So I counted that mainly up to the operation of it, being cautious and careful in the first launches and then getting a little less so as we went on, and then it also began to get difficult because lost strength to stretch it back. Our main error was having to stretch it back at the same initial velocity, so that was probably the main error in the differences between our values. Other errors we encountered, though, were improper operation of the launcher. The ball would hit the sides of the slingshot sometimes. Pulling it back was the main source of error. Reading the landing position might have been an error that we encountered. And then just overall, the power of the slingshot made it a lot difficult, really difficult, just because it shot higher than we were able to measure and farther than we were able to measure. So if it weakened, I think to make the experiment more realistic as a whole, just to have a weaker projectile launcher and then maybe even a bigger and heavier projectile of itself to just have a smaller range. And then kickers on a football team just maximize their kicking abilities through knowing what angle to kick at to match the area of, to match the what the situation calls for. So yeah, overall I think our conclusions were justified, that we found our objectives. And yeah, overall it was a good experiment. So thank you.